Hello, my name is Phil from Maya HTT. In this video, I'll show you how to perform a random base excitation simulation using SA Toolkit Pro Advanced. Random base excitation testing is prevalent in the automotive, electronics, and space industries. We'll be using SA Toolkit Pro's random processor to simulate the random response of a medium-sized spacecraft model. SA Toolkit dramatically reduces solution time while increasing results accuracy. It's over 3,000 times faster than its competitor. We'll excite the spacecraft in the lateral direction using a notched acceleration PSD function. We'll review the output peak acceleration and margin of safety contour plots in SimCenter FreeMap, as well as the power spectral density response function plots. Note that SA Toolkit results can also be exposed in SimCenter 3D Desktop. Let's begin by opening the model in FreeMap. Here you can see the spacecraft assembly, consisting of the bus, the various payloads, as well as the launch vehicle adapter, the lower interface of which connects to a constrained central node via a rigid element. The FEM of the spacecraft contains about 130,000 elements, pointing to both metallic and composite materials, as well as about 160,000 nodes. The Analyses tab already contains a SimCenter Nastran Solution 103 solution set, which will be used to calculate the modes of the structure. Under Bulk Data, param OGeom is checked on, and under Manual Control, param RSOpt1 is specified, and the USET1U2 card points to the degrees of freedom that will be excited, as well as the excitation node ID. Expand the modal buckling node and see that 35 modes were requested. Under Output Requests, displacements are requested for all nodes, whereas stresses are requested for a FreeMap group. Next, let's solve this Nastran solution. On my machine, this took about 5 minutes, and the OP2 file size is about 1.8 gigabytes. Start SA Toolkit. Its interface automatically docks like a regular FreeMap pane. When you open the results file, you'll see the data blocks it contains. Next, we'll create FreeMap groups that SA Toolkit will read to compute stress margins of safety. One group of elements for each material. Next, we'll create a group of nodes at which we'll request acceleration PSD function results. Once all our groups are defined, we can import them into FreeMap using the Import from Active FreeMap Model command. Now open the random processor. Begin by specifying the base acceleration power spectral density. You can define up to 3 load cases, each with 1 to 3 excitations. For each load case and excitation, you can manually specify the points or import a function from an external file, which is what I'm doing here. To validate your PSD, you can plot it. For this demo, the acceleration PSD is defined in g² per hertz. The scale factor must convert the PSD function units to consistent acceleration units. In this case, we set it to 9,810 millimeters per second squared. We move on to the next step. In the Frequencies dialog, you can specify which modes to use in the modal superposition, as well as the upper and lower frequency limits. Here we'll use all 35 modes in the OP2 file and integrate between 10 and 100 Hz. In the Modal Damping tab, you can specify the modal damping in the form of an amplification factor, Q. In this analysis, we'll use the default 2% viscous damping ratio. In the past, engineers hand multiplied RMS results to obtain the 3 sigma responses which are typically required in the space industry. In this tab, the confidence level of the calculated peak response can be directly specified, making this tedious manual step no longer necessary. We'll use the Maya PDQA method of von Mises stress computation, which is much faster than the heritage Sigelman method used by the competition. To obtain stress margins of safety for elements that point to isotropic materials, stress cases must be defined using the materials group that were created in FEMAP. For each stress case, safety factors and allowable strength must be specified. Here I'm showing how to create the first stress case for components that are made of aluminum. Click on Output Requests to select the results you want. The availability of these results is dependent on the results that are in the Nastran Solution 103 solution. Contour results can be written in text, Excel, FEMAP neutral, and OP2 file formats. PSD results can also be written to an HTML page. Groups of elements or nodes can be selected to focus on specific areas of the model. Now let's solve this random event. For this demo, we've requested peak acceleration contours for the entire model, acceleration PSDs for the acceleration group nodes, margins of safety for all composite elements. No other software computes random composite failure metrics, as well as margins of safety for all elements included in the stress cases you defined. On my machine, this took about 23 seconds to complete. Notice that no excitation frequencies were specified. This is because SAToolkit automatically defines them, so you don't have to. Now let's look at the contour results in FEMAP. Load the peak acceleration along the x-axis. We use the FEMAP process command to convert millimeters per second squared to Gs. The peak x-axis acceleration response of 197 Gs occurs near the antenna feed. This is closely followed by the top of the solar panels. Next, load the peak acceleration magnitude. This is the peak phase-consistent acceleration magnitude response computed by the random solver for the x, y, and z components, and which is 263 Gs. In the past, engineers had to manually compute the root sum squared of the RMS x and y and z components, which is incorrect since there is no phase information in the RMS results. Now we're loading the peak von Mises stresses for the first stress case, aluminum components. On the Results tab, set the shell and beam location to maximum. The maximum stress is very high, is over 7,000 megapascals, which is much too large. Our notching seems inadequate. To assess the stress magnitude, it's also convenient to look at the margin of safety results. There are results for each of the stress cases we created and which we enveloped using the FEMAP tools. Load the peak margin of safety. And let's invert the colors such that the smaller margins are red. And let's specify an overflow value. You can see that the minimum margins of safety are negative, which means that the stresses are much too high in many regions. These confirm that the input function notching wasn't successful. You can use the FEMAP enveloping command to envelop any result like margins of safety for all the stress cases. Lastly, let's look at the peak ply failure indices. A few areas of the group have indices that are larger than 1, which again indicates that the stresses are too high. Finally, let's review the power spectral density results. These can be visualized in the FEMAP charting pane, but in this case we'll look at the HTML page generated by SAToolkit. There are 52 plots, 4 for each of the 13 nodes in the group we selected in the output request dialog. There are 3 plots for the translational PSDs, as well as the phase-consistent magnitudes of the translational PSDs. In this tutorial, I showed you how to perform a random base excitation simulation of a medium-sized spacecraft model using SA Toolkit Pro. I used its random processor that is 3,000 times faster than the competition, which produces peak results that correspond to the desired confidence level, including phase-consistent vector magnitudes and von Mises stresses. I validated the notching of the input PSD functions in various ways. Thank you for watching.